Hello, we are Group 7 and welcome to our presentation on predicting heart attack risk through machine learning. Our problem. The problem we've chosen to deal with is a problem that affects people all over the world. It is especially a problem for those in wealthy countries like US and Canada. Our problem is heart disease, its causes, associated risks, and what people can do to prevent it. We will be creating multiple machine learning models and performing other machine learning related activities like determining feature correlation to learn more about the problem of heart disease. The dataset. Our dataset is a dataset we sourced from Kaggle called Indicators of Heart Disease and has CSV files from both 2020 and 2022. The dataset here was originally sourced by the CDC via telephone surveys, and we decided to go with the 2020 variant. Aside from the target variable, our dataset has 17 features. These features include BMI, physical health, and age, to name a few. Some of these features need pre-processing to make them numerical, like general health, which comes as good, very good, etc., race, and diabetic, which could be borderline. Objectives. Four main objectives were kept in mind when working on this project. We want to be able to determine features most correlated with negative heart health, develop a model that is able to predict heart disease risk, implement machine learning techniques we learned in class, compare multiple machine learning models, and encourage people to lead healthier lives.
Our approach involved four key steps: data preprocessing, model selection, model evaluation, and results visualization. We cleaned the dataset, selected random forest and neural network models, assessed their performance using metrics like accuracy, precision, and F1 score, and created visualizations highlighting feature importance and model comparisons. For data preprocessing, we used the following techniques: binary encoding, which is converting categorical values like yes and no into numeric binary values of zeros and ones. This ensured that the data was in a format suitable for machine learning models. Ordinal values, which are features with a natural order, are mapped to integers, which reflects its progression. One-hot encoding for categorical variables with multiple categories but no inherent order or progression. This creates a separate binary column for each category, allowing the model to treat them as distinct and independent features. Scaling and normalization were used for continuous variables. By improving the scaling, models that rely on distances or gradients like neural networks could accelerate convergence and improve optimization. Feature engineering, we also engineered new features to enhance the model's predictive power. For example, interaction terms and higher order features could help capture nonlinear relationships between variables, improving the model's capabilities. To handle binary categorical features, I converted variables like heart disease, smoking, alcohol drinking, stroke, difficulty walking, physical activity, asthma, kidney disease, and skin cancer into numerical values of zeros and ones. Some features in our dataset had natural order or ranking, which I captured through ordinal encoding. BMI was categorized into underweight, normal, overweight, and obese to reflect the increasing weight categories. Then they were assigned numerical values in ascending order. Gen Health was mapped from values 1 to 5 based on responses ranging from poor to excellent, capturing the progression of health quality. Age category was encoded from 1 to 13, reflecting age groups. Diabetes was transformed into a scale of 0 for none, 1 for borderline, and 2 for yes. Sleep time was categorized into undersleeping, normal, and oversleeping. With one hot encoding, this was used for features with multiple categories, but no inherent order such as race, so we transformed race into separate binary columns. For feature engineering, which is the process of creating new features, I used a correlation heat map to identify the correlations between variables. This low correlation between most features indicate that multicollinearity is not a significant issue in our dataset, making it a good scenario to create interaction features. To better capture the complexity of the diabetic feature, we split it into two distinct features, one for progressive diabetes explained earlier, and a separate binary feature to indicate whether an individual had diabetes during pregnancy. We generated a BMI squared feature to account for any nonlinear relationships. The higher order feature could help the model better capture the effects of BMI on the target variable. Chronic conditions is the sum of stroke, asthma, kidney disease, skin disease, and diabetes. This provides a single feature that reflects the overall burden of chronic conditions, which may be more informative than each individual condition. A new feature called smokes and drinks was also created using an AND operator. This interaction may have an amplified effect on heart disease. And lastly, active good health is a combination of physical activity and gen health, which are both key factors in heart disease prevention.
For data preprocessing, we also use scaling and normalization. I scaled BMI using Z-score normalization since it matched the Gaussian distribution. Mental health and physical health will use log transformation since it's skewed to the left. Before normalization, our dataset features 70 indicators like BMI and sleep time, while values on vastly different scales. This imbalance risks certain features dominating the models, leading to a more biased results. After normalization, we rescaled the data, bring all features to a similar range. This adjustment allowed models to process the data more effectively, improving both accuracy and convergence speed during the training. Overall, normalization enhanced model performance and highlighted the critical role of preprocessing in ensuring reliable predictions.
We developed and trained a random forest classifier and a neural network model using the processed data to predict the likelihood of a person having a heart attack. We chose the random forest classifier because it is adaptable and robust. This model is non-parametric, making it possible to apply a variety of data sets. Additionally, it can handle a variety of data types and outliers, making it reliable to use. However, it is more computationally intensive, requiring more memory and time. Additionally, it is like a black box, as it is difficult to understand the logic of each prediction. Similarly, a neural network model provides adaptability in datasets and increases computational power through parallel processing. This model makes up for some of the random forest's disadvantages as it can compute faster. However, it is also computationally intensive in memory, and it is a black box model. Overall, the models have more capability in understanding the features in the dataset despite the disadvantages.
Here are the results that we got from running the random forest model. The model achieved an overall accuracy of 90.15% in classifying patients as having or not having heart disease. Its precision in identifying positive heart disease cases was 39.95%, though the recall or ability to detect actual positive cases was slightly lower at 30.05%. Importantly, the random forest had a strong ROC-AUC score of 0.836, suggesting good ability to distinguish heart disease from non-heart disease patients. The low precision and recall scores suggest that the model has issues with false positives and false negatives, and the low F1 score may suggest overall model performance issues. The neural network model achieved an accuracy of 89.35%, slightly lower than the random forest model, and it struggled a bit more with precision, correctly identifying positive cases only 36.25% of the time. The recall was also on the lower side at 31.82%, and the neural network's ROC-AUC score of 0.832 indicates a reasonably good but not exceptional discrimination between the two classes. Comparing the two models, the random forest appears to be the stronger performer based on the evaluation metrics. Its higher accuracy, precision, and ROC-AUC indicate it may be better suited for this heart disease prediction task. However, both of these models struggled with overall performance, and a contributing factor may be the imbalanced dataset, where heart disease is such a minority class that the model overcompensates by predicting no heart disease class much more often.
Reflecting on our goals, we can confidently say that our project successfully met its core objectives. The models demonstrated a strong ability to analyze patterns in healthcare indicators and highlighted correlations that could guide both healthcare professionals and individuals in understanding and mitigating risks. Our project has shown that machine learning tools are great promise in aiding fight against heart disease, while there are room for further refinements. The progress we've made marks an encouraging step towards building tools that can contribute to a better life and health outcomes and greater awareness of preventive care.